All right, here's the video for our polynomial part 2, or our chapter 6 part 2 study session. So first problem we're going to go through here is just estimating, given a graph, our x-intercepts, local max, local mins, lowest possible degree, and then our domain and range. So let's start with the x-intercepts. So if we look at this graph, for x-intercepts, we're looking for when it crosses the x-axis. So we have 3 of them. So now estimating, okay, when we're estimating, I just want something close. Okay, so if we look at that, if we work from left to right here, that first one doesn't quite make it to the -1. So something close, I would say -0.9. And then since it's an x-intercept, we have to write it as an ordered pair, so -0.90. And for that next one, when I look at that one, okay, you know, halfway is about there and it doesn't quite make it there, so I'm going to say 0.4. So 0.40, and then finally that last one, 3, okay, it looks like it crosses right in the middle between 3 and 4, so I'm going to say 3.50. Now, remember, if I was to ask for zeros instead of x-intercepts, okay, in that case, you're just telling me the x values. Okay, so know the difference if I was to ask you for x-intercepts or zeros. There is a difference on how we write them. Okay, local maximum then we're looking for a high point. Okay, and then it looks like I only got one of those. And whenever we're doing a high point again, I'm looking for the y coordinate. So how high does it make it on the y-axis? Now if I look here, okay, we have a scale of 2 here. Okay, so at halfway mark, that's 1, and it looks like it makes it about halfway between that 1 and 2, so I'm going to say 1.5 for that maximum. Now remember, when I grade these, I'm looking for a range. So like if we had a graph like that, you know, I'd probably accept 1.4, 1.5, 1.6. You get any one of those values. Okay, local minimum then, looks like we're going there. Okay, so -6, -7 would be there. Looks like it'd be a little bit below that, so let's say -7.2. Okay. All right, so now, lowest possible degree. Again, when we're looking for lowest possible degree, we're going to look at the number of turning points. Okay, so I have 2 turning points, and remember, the number of turning points is always 1 less than the degree. So then we have a lowest possible degree of 3, given what we see for the graph. Okay, domain, again, looking left and right, or what x values can I plug in and get something back. In this one, it's going left and right forever, so x is the element of all real numbers. Okay, range, we're talking y now, so up and down. How far up and down would this graph go? It goes up and down forever. Okay, so in this case, y is an element of all the real numbers as well. Okay, so that was estimating, given a graph, specific things that we asked for. All right, so for the next one, sketch a polynomial of 6th degree with the following characteristics. Okay, before we move on, what I'm gonna do is I'm gonna figure out the end behavior. Okay, so 6th degree, I'm either going both up or both down since it's an even degree. Now we do need to look here. A is positive, so that tells us our end behavior should both go up. Okay, so that's good for the 6th degree, and A is positive. Now, there's a triple root at -5. Okay, so we're going to go to -5. And 1, 2, 3, 4, 5. Okay, so there's a 0. A double root at 2. And a single root at 5. So I know that those are the only 3 spots that this graph will cross through the x-axis or touch. So let's just label those real quick. We said this was a triple, 2 will be a double, and then 5 will be a single. Okay, so make sure we do the proper graphing of those zeros. So there are additional turning points at -2, -7. So let's plot those points. Okay, so we have a turning point there and a turning point at 4, -4. Okay, so when I'm doing this now, again, we look at our end behavior. So I'm going to start in quadrant 2, and then I need to go to my first root, which we said was a triple root. In that case, we're going to sweep through that point. Okay, and then I have that next point, which is a turning point, so we're gonna make a turning point there. And I gotta go up to that next 0, which is a double root. Double roots, we just touch the x-axis there. Another turning point. And single roots, we go straight through. Okay, so I have the proper end behavior. I got the right roots represented with the triple, double, and single, and I have my turning points where I specified. All right. Okay, now another sketch. Okay, sketch the graph of a polynomial function that has 4 roots where all of them are real and 1 is a double root. Okay, so let's write this down. We got 4 roots. Okay, and 1 has to be a double. Okay, so that's representing 2 of those 4 roots. So there's a couple options we can go with in this case. You can make a single root and a single root. And again, combining those, that gets us our 4 roots we need. Another option we have, because one of them has to be a double, the other 2 does not matter, so we can make it 2 doubles if we wanted to, and that would combine to give us 4 roots either way. Okay, now that we know what type of roots we're going to use, let's look at our end behavior. Okay, so as x approaches positive infinity, f of x is approaching negative infinity, which is saying as I go right, I need to be going down. And then as x approaches negative infinity, f of x is approaching negative infinity, so as I go left, I'm going down. So I need to have an end behavior that looks like that. So starting in quadrant 3, ending in quadrant 4. So I'll do one of each here. So we got the 4 roots where we do the double, single, single. So we need to have 3 points on the graph, 1 being a single, 2 being the singles, and 1 being a double. So, and which one you make the double, I do not care. For this case, I'm just gonna go single. Let's do a single here, and we can make this one a double. Okay. So when I grade these, I'm looking that you have your 4 roots represented. Okay, so here we got 1, 2, 3, and 4. So there's your 4 roots represented. The proper end behavior, which should both be going down. And then finally, the number of turning points. Okay, number of turning points, if it's a degree 4, we have 4 roots. So degree 4, we should have a maximum of 3 turning points. All right, now let's go ahead. Let's do it a different way. Let's do 2 doubles. Okay, so in that case, I still start in quadrant 3, got a double root, and I need to come back up and hit this other double root and have the proper end behavior. Again, that's 2 4 roots that we're representing with 2 double roots. 1, 2, 3 turning points, which we can have when there's 4 roots. All right, so again, those are sketches. There's a lot of different options you could have gone with. I'm looking for the end behavior and that you have 4 roots represented on your graph. All right, so another graphing one. Now I actually give you the function. When I give you a function like this, then we need to determine our zeros. And to determine our zeros, you take each of the factors, set them equal to 0, and solve. So we got x equals 3, x equals negative 3, and x equals negative 2. Now, one thing to remember though, x minus 3, that quantity squared. So this is a double root for that 0 of 3. So we have our 3 roots at 3, negative 3, and negative 2. Now what I would do, label that double root, okay, and that's at positive 3, so there's our double root there. Now with that, okay, this is representing 2, this is 1 root, so adding those together, we get a degree 4 polynomial in this case. Okay, so our end behavior then, since it's even, will go in the same direction, and then we got to look at the leading coefficient. It's positive, therefore going in the same direction, and then positive leading coefficient, they will both be going up. So we need to start in quadrant 2, end in quadrant 1. Okay, so we have single and a single. Starting in quadrant 2 then, just starting up here, we need to go through that 0, got to come back up and go through that 0. And then whatever you do at this point, it does not matter. This is why we're sketching these. But the important part is we have a double root there. and we have that proper end behavior. Okay, and then since it's degree 4, we need to look at our turning points. We have 1, 2, 3 turning points, which we can have since it's always 1. The maximum number is 1 less than the degree. All right, that was sketching that function. All right, so using your graphing calculator to graph, we're going to graph that function and then find the following features of that graph. And we'll round to the nearest tenth when we do that. So bring in the calculator here. And in order to do this, we always go to y equals, and you're going to type in that graph. Now x cubed, you bring in x with that button. On the TI-84s, it's xt theta. It's right next to that alpha button, just like on this one. And then the cube, caret top, cube. Once you put your exponent in, you got to bring it back down. So hit the right arrow, minus 7x squared. Again, bring it back down, plus 15. Okay. Now I got my scatter plot on for a problem we will do later, so I'm going to turn that off for right now. Okay. Then we just hit graph, and if nothing shows up, again, you always hit zoom standard. Okay, it's zoom 3 on the iPad, zoom 6 on the calculators. So zoom 3. So there we have our graph. And the first thing we're going to look for is our zeros. So anytime we're trying to find these specific features of a graph, it's always second trace, and we're going to calculate a 0. Okay, now it's asking for a left and right bound. Okay, so we're going to look at that first one working from left to right. It looks like it's between -2 and -1. So I'm going to have a left bound of -2, which the calculator is asking for right now. Hit enter. Now the calculator is asking for a right bound, which I will say -1. And there we have it. Y equals 0. So my 0 is x is equal to 1.3. Because again, we are rounding to the nearest tenth. Okay, for that next one, you go hit second trace again. We're searching for a 0. Next one looks like it's between 1 and 2, so a left bound of 1, right bound of 2. Y is equal to 0, so the next one is x is equal to 1.7. And then finally that last one, again, second trace, searching for a 0. Looks like it's between 6 and 7, so a left bound of 6, right bound of 7. We got a 0 of 6.7. Okay, so there's our zeros. Let's go ahead, let's find those local max and mins. Now, this is where it's a little tricky with this one, because we can't see those local max and mins, but what I do know is you can tell that it's a turning point at the top there if we're looking at the max. Okay, so it shouldn't happen on the test, but we know that 0 is going to happen somewhere close to the y-axis there. So second trace, you're looking for a maximum. Okay, now I'm just going to use those x-intercepts that we have. It's between -1 and 1. So left bound of -1, right bound of 1. Okay, 0, 15, and again for those maximums, we're looking for the y-coordinate, so we just have a maximum of 15. Okay, now for that local minimum, I know it's going to be between those other two zeros, okay, between that 1.7 and 6.7. Again, we can't see it right now, but we should know that it's down there since the graph is coming back up. So I'm going to do second trace. We're finding a minimum in this case. Okay, and let's go 2 to 8. So left bound of 2, right bound of 8. So it's basically what we're telling the calculator, when x is 2, when x is 8, everything in between, where's the lowest y value you get. Okay, so again, on the test, or you will not see one like that. You should be able to see those max and min specifically on the test, but it's the same idea, left and right bound. In this case, that minimum is -35.8. Okay, so domain and range then. Domain, how far left and right we would go. It's going to go left and right forever, so x is an element of all reals. Range, it's an odd degree, so it's going to go in, end behavior goes in opposite direction, so it'll go up and down forever. So y is an element of all the reals as well. Okay, so that was finding features of a graph. given the function using your calculator. Okay, so the next one, find the equation of the function in factored form. Okay, so it looks like we have a cubic function here. And in order to find the equation of this, we're going to use our zeros. Okay, we have a scale of 2 in this case. So let's figure out those ordered pairs. So this one is -4, 0, -2, 0, and then finally 2, 0. Okay, so those are our zeros of the function. And again, y is equal to a times x minus p, x minus q, x minus z, whatever. Okay, the p, q, z, whatever variable you decide to use, that's representing the zeros. So in this case, y is equal to a times x minus -4, x minus -2, and x minus 2. So just rewriting those better, x plus 4, x plus 2, x minus 2. So we have the factors of our equation. Now we need to figure out the a value, and again, to figure out that a value, we're going to use that extra point that we're given. So in this point is 0, -2. So we're going to take that. That's my x, that's my y, and we're just going to take that and substitute those in. So in this case, we got -2 is equal to a times 0 plus 4, 0 plus 2, 0 minus 2. So -2 is equal to a times 4 times 2 times -2, or -2 is equal to -16a. Solving for that a now, you should get an a value of 1/8. Always simplify if it's possible. Now, we're not done yet, because now I got to take that a value and plug it into a. So my final answer for this one, y is equal to 1/8 times that x plus 4, x plus 2, x minus 2. So any case where you're trying to find, you need to find a, you can leave that one in factored form. Okay. All right, so for the next one, write a polynomial function of least degree that has real coefficients and a leading coefficient of 1 that has the following zeros. So in this case, we have 3 zeros, 1, -3, and 4. Okay, so there's a couple routes you can go with this one. We're going to write these out as factors. We have a leading coefficient of 1, so you don't have to worry about a at all. X minus 1, x minus that -3, and then x minus 4. So just simplifying that, x minus 1, x plus 3, x minus 4. Okay, so first option, I'm not going to go through it. You could just multiply those 3 factors out and get that polynomial that you need. But what I'm going to do is I'm going to use the sum and product with those 2 zeros. So sum again is adding, so 1 plus -3, which is -2, and our product 1 times -3, which will give me -3. So what you need to remember then, f of x is equal to x squared minus the sum of x plus the product. Okay, and again, this is using 2 zeros to help us get the quadratic for those 2 zeros. Okay, so we use the 1 and -3, so basically we're going to be multiplying those 2 out and just doing a shortcut. So again, x squared minus the sum, which we said was -2, so minus -2 will be plus 2x, plus the product, which was -3. So basically what it comes down to, if we were to multiply that out, that is what you would get. Okay, finally, we still need to multiply that trinomial times the binomial. So x squared times x, we will get x cubed minus 4x squared. Okay, done with the x squared. Taking the 2x now, plus 2x squared minus 8x minus 3x plus 12. Combining like terms then, x cubed minus 2x squared minus 11x plus 12. Okay, so when you get problems like this, when all the roots are zeros or all the roots are real, it's not too bad. Now, let's do another one where we get imaginary roots. Okay, so we want the real coefficients, leading coefficient of 1 with the following zeros. So we got x is equal to 5, and I'm going to put together my real ones. So 5 and negative 1. Then I have the negative 3i. Now, the one thing you need to remember with these ones is that imaginary solutions always come as conjugate pairs. Okay, so I need the conjugate pair with negative 3i, which is positive 3i. So you are not given all of the roots in this case. You need to know that you need the conjugate pair for any imaginary. Now, what I'm going to do is I'm going to use the sum and product with 2 different times. Okay, one time with the 5 and negative 1, one time with the negative 3i and 3i. Okay, so I'll do the real ones here in blue. So sum, that's saying 5 plus negative 1, which will give me 4. Product, 5 times negative 1, which will give me negative 5. So then for our imaginaries then, the sum, negative 3i plus 3i. So think, if you're having troubles with imaginaries, think of it, negative 3x plus 3x. Okay, they cancel each other out and give us 0. Product, negative 3i times 3i will give me negative 9i squared. Negative 3 times 3 is negative 9. I times I is I squared. But then you need to remember, I squared is equal to negative 1. So that's saying negative 9 times negative 1, or 9. So writing this function then, f of x is equal to, and again, x squared minus the sum, and I'm dealing with my real roots, so minus 4x plus the product, which would be minus 5. Okay, so that's the quadratic that I would get from those 2 real zeros. For the imaginary zeros, x squared minus the sum, which was 0, so I'm not even going to worry about writing that 0, plus the product, so plus 9. Now, we still need to multiply that through. So f of x is equal to x squared times x squared, which is x to the 4th, x squared times 9 plus 9x squared. Okay, done with the x squared term. Negative 4x times x squared will give me minus 4x cubed, and then minus 36x. So done multiplying with the negative 4. Taking that negative 5 now, minus 5x squared minus 45. Combining those like terms then, x to the 4th minus 4x cubed, x squared's there, we got plus 4x squared minus that 36x minus 45. There is our answer. All right, so again, remember the big thing here, imaginaries always come as conjugate pairs. Okay, so now let's run a regression. Okay, data represents the average claims paid per policy in hundreds for automobile insurance in West Fargo in the years 1971 to 1980. Now, it doesn't say that, but we're going to say let X be the number of years since 1970. Okay, so when you're doing that, it's very important to read carefully. Okay, because for the years then, since X is the number of years since 1970, 1971, that's 1 year. 2, 3, 4. Okay, because these are the values that you will type into list 1 on your calculator. Okay, so we're going to do the scatter plot. And you always just need the first quadrant again. And now remember, you need your labels, you need your scatter plot, and then your x min max, y min and max. Okay, so the x, let x be the number of years since 1970, so that's going to be our label here. Okay, and our y is the cost. Okay, so need to go to our calculator, and you need to type in that information. Okay, now this is the 4th time, I think the 4th time that we've done regressions. Okay, so in this case, again, you always go to stat, edit, you enter the information. I have it entered in already. Okay, so, but make sure when you're entering it in, double check that it is all entered in correctly. Now, to get our scatter plot, again, I'm going to clear that. You need to make sure your scatter plot is on. Okay, so second y equals, let's turn our plot on. So now that it is on, we go ahead and we hit graph. Now, again, you probably won't see anything, but you always need to hit zoom stat. Okay, so on the iPad, zoom 5. On the calculators, it's going to be zoom 9. Okay, so then we get our scatter plot, and we are just going to sketch what we see. Okay, so there's our scatter plot. And then to get the x min and max, y min and max, you're going to hit window. Okay, we had an x min of 0.4, x max of 10.6. Y min, let's just round to the tens place, 40.6. Sorry, 40.5. And a Y max of 119.9. Okay, so there's our scatter plot. Okay, the next problem is always determining what type of regression you need to run. Okay, so when you look at this scatter plot, that should be the indicator of what type of regression you can run. Now, what I always look at is the end behavior. Okay, it looks like they're going in opposite directions if you were to draw a line through that. Okay, so we're limited to a linear regression or a cubic regression in this case. Remember, degree 1, degree 3. Now, I see those turning points. Okay, it's not looking like it's a straight line. It looks like it turns a little bit in the middle. So in this case, I'm going to run a cubic regression. And in order to do that, you always hit stat, calculate. Okay, and we're going to do a cubic regression. List 1, list 2. Okay, so then from there, you take A, put it in A, B into B, so on and so forth. So in this one, y is equal to 0.3005. And we always go to 4 decimal places minus that 4.2063 x squared plus 20.9473x and then plus 26.9303. So there is our cubic regression. Okay. Now state the coefficient of determination to 4 decimal places. That's that r squared value. So r squared is equal to 0.9922. Now, what you should do, okay, is just double check that that is the proper regression to run. Okay, so remember, this coefficient of determination tells us how strong of a fit that equation is to the scatter plot. Okay, that's a very, very strong fit. But still, let's just double check and let's run that linear regression. Okay, now with linear regressions, you're looking at the correlation coefficient, which is the R, which is 0.919, which is not as strong as the 0.9922. Okay, so right there it tells us that we ran the right regression to start with the cubic regression. Okay, all right, so now the last thing, make a prediction for the cost of insurance in 1985. Okay, so we're given a year, and it's 1985, and X is the number of years since 1970. So in this case, X is equal to 15. And what we're going to do is we're just going to plug that into our regression equation. Y is equal to 0.3005 times 15 to the 4th minus 4.2063 times 15 cubed plus 20.9473 times that 15. Oh, I got my exponents wrong here. 3, 2, 1, and then finally plus that 26.9303. Now, when you are doing this, okay, what I would do is put everything in parentheses on the calculator. So put that in parentheses, put that in parentheses. Okay, so we got 0.3005 times 15 to the 3rd. Oh, Here, let's start over here. 0.03005 times 15 to the third. Okay, get out of that exponent. Okay, that's your first term. You're going to subtract 4.2063 times 15 squared. Close that parentheses. Plus, parentheses now, 20.9473 times 15. And then finally, plus, you don't have to worry about the constant because you're not doing any type of multiplying, 26.9303. Hit enter, and we get y is equal to 408. We're just going to write this all right here. Okay, and it doesn't specify what to round to. So, make a prediction for the cost of insurance in 1985. Okay, they had all theirs to the hundredths, so let's go ahead and round to the hundredths. 408.91. Okay, and this was always in terms of hundreds. Okay, so 408.91 hundred. Or if you wrote it, you just multiply that by 100. 408.91. So $40,891. All right. So that is the review video for our Chapter 6 Part 2 test. If you have questions on this, make sure you let me know. And have a good day.